Okay, let's talk about power series and functions. Very similar to infinite series, we're just now going to throw in the variable x. So a power series, by definition, is an infinite series of the form the sum from n equals 0 to infinity of c sub n x to the n, where c is for your coefficients, and then those are going to be your constants, your numbers, very similar to the series we had before. And then x to the n is what we're adding in. So now we're making this an infinite polynomial. So a power series is an infinite polynomial. It's very specifically x to the power of n, where n is my counter, which means it's a polynomial. There's no square root of x involved in here. Or it could very well be shifted. Remember that x minus a, if you have that inside of parentheses of any function, that is a shift to the left or right, where c sub n are the coefficients, and then typically what we call as the center is that a value, which is the constant, so where it might be shifted. I thought I'd show that to you guys first in Desmos, so you can see what I have there in orange. That first graph, there we have it, is some polynomial. Now this one's not infinite because I decided to stop at 25, but it is some polynomial right there. And then if I were to shift that polynomial either to the left or to the right, that a is now changed in center. It started off centered at 0, and then that a just shifts the polynomial a little bit. Okay, that is a power series, an infinite polynomial. So an example was that the sum from n equals 0 to infinity of just x to the n. In this case, all of my coefficients are 1. So in this case, I just have 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th forever. It is an infinite series that is called a power series. This particular example that I have here is a geometric series with a ratio, instead of r, it's now x. So remember in the geometric series that we talked about, if we had a series, not a power series, but let's say a series, the sum from n equals 0 to infinity of 1/2 to the power of n, that was geometric. And in this case, my r was 1/2, which was less than 1, so it converged, and it converged to a on 1 minus r, where a was the first term of the series. And it only converged if that absolute value of r was less than 1. So now you should see that this is the exact same thing, except for instead of a number, I have a variable for this function. A power series can be a function. So now I know that this would converge if the absolute value of x was less than 1, and it would diverge if the absolute value of x is greater than or equal to 1, because it's a geometric series. So there are, of course, other examples of power series. I could have the sum from n equals 1 to infinity of, let's say, -1 to the power of n times x to the n. I could make this an alternating series. If I started it off at 0, let's say I would get 1, and then -x, and then plus x squared, and then -x cubed, and so on. That is another power series. Another example of a power series could be something like the sum from n equals 1 to infinity of n times x to the power of n. And if that were the case, I would end up with 0 plus 1 times x plus 2 times x squared plus 3 times x cubed. It's another infinite polynomial with different coefficients. You could also have some other ones where perhaps you have built-in fractions, the sum from n equals 1 to infinity of, we can even maybe shift our center, let's say x minus 1 to the n over the square root of n. If I plugged in 1, I would get x minus 1, plus if I plugged in 2, I would get x minus 1 squared over the square root of 2. And so in that case, your coefficient was 1 over the square root of 2, etc. So these are some examples of power series. In general, what you want to think of in your head is a power series is an infinite polynomial. That's really truly what it is. Okay, so since the terms in a power series involve a variable x, it means that sometimes the series is going to converge and sometimes it's going to diverge. Think of it like a domain of a function. Sometimes I can plug in the number, sometimes I can't. Here similarly, but now for converges and diverges. So the idea is the power series, whatever it might be, either shifted to a different center or centered at 0 with whatever the coefficients may or may not be. The series satisfies exactly one of the following properties. Either the series converges at x equals a and diverges for everything else. Here's why it will converge at x equals a. If I plugged in x equals a, that would get 0. If you add up infinitely many zeros, you get 0. So that still converges. So it's going to converge at x equals a. So maybe it possibly converges at x equals a, and that's it. Maybe that's the only number I could plug into the infinite polynomial and get a convergent series. Maybe it diverges for everything else. Or maybe the series converges for any number I want to plug in. I can plug in a, I can plug in 2, 25, 75, 34, negative 12, any number I want. It's possible that it converges all the time. Sometimes that happens. It's also possible it converges for some smaller interval. Okay, some smaller interval converges if x minus a is less than r, that absolute value there. That would be some small interval of convergence. It is possible that it converges for a collection, like maybe from -1 to 1, but then diverges outside of that, just like the geometric series we did before. All right, so those are the examples there. So here's a picture of those 3 possible properties. It maybe converges at once, diverges everywhere else. Maybe it converges everywhere, or maybe it only converges on some small interval of x values. And that's why we called A the center, is because A will be the center of that interval of convergence. Okay, let's do some examples. Let's find the interval of convergence. Does it converge for only one number? Does it converge for all x values? Or does it converge for some smaller amount? So there's lots of different ways we can do this. We're trying to figure out if a series converges or diverges. So we have all of our tests from chapter 5, the divergence test, the integral test, p-series test, comparison test, limit comparison test, alternating series test, ratio test, root test. There was a lot. One of the things we mentioned, though, in that chapter at the end of chapter 5 last time is if you have a factorial, you should do the ratio test. And that's still true, even though this is now a power series. So I am going to do the ratio test here. And I'm going to remind you what the ratio test is. It's take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. In the ratio test video, we ended up ignoring that absolute value because all of our terms were positive. But here, I have to keep that absolute value because x is unknown. It might be a negative number. I got to keep that absolute value. Okay, all right, but the idea is still the same for the ratio test. I do the limit as n goes to infinity, keep that absolute value. I first plug in n plus 1 everywhere I see an n. Only where I see an n, and then I divide by the original, so divided by the x to the n over n factorial, and you know how to divide by fractions. That means I multiply by the reciprocal. Keep the absolute value. Now we do the algebra. When I do the algebra, I'm going to give myself some space here. When I do the algebra, this becomes the limit as n goes to infinity, absolute value, x to the n, x to the 1, n factorial. And remember that n plus 1 factorial is n plus 1 times n factorial. X to the n plus 1, I broke up that exponent, and then I can see some things canceling. So x to the n is gone, the n factorial is gone. This limit becomes the limit as n goes to infinity of the absolute value of x over n plus 1. That absolute value was important because x is unknown and I have no idea if it's positive or negative. I need to make sure I keep that absolute value to be safe. Now, the ratio test had 3 bullet points. The first one was if the limit is less than 1, the series converges. If the limit is bigger than 1, the series diverges. If the limit was equal to 1, this test is inconclusive. So in this particular case, I really want to know when this is less than 1. That was the goal. When is this guy going to be less than 1? Because I want to know where it converges. I'm not looking for an interval of divergence. I don't care about divergence. If it diverges, it's useless to me. I want convergence. I want an actual answer here. So if I want my power series to converge, I want the answer to the ratio test to be less than 1. So that means I have that limit, I want it to be less than 1. Let's actually take that limit. This is the goal. Maybe I should write that in a different color. I want it to be less than 1. That's the goal. I'm going to actually take the limit and see if it's less than 1 or not. So I'm taking the limit now as n approaches infinity. X is unknown. It's some number. X is a number. It might be 5 million. Let's just say, I don't know, maybe it's 5 million. But this is bigger because n is approaching infinity. So it doesn't matter what x is, this will be bigger. So I'm going to have x divided by a really large number, which no matter what is going to be 0. We said I wanted it to be less than 1. Is it less than 1? Yes. Is it always less than 1? Is 0 always going to be less than 1? It is. Always. No matter what x value, no matter what x was, the answer to this ratio test was convergent. No matter what x was, the answer to this ratio test was converges. Therefore, my interval of convergence is from negative infinity to infinity. This converges for all possible x values. Plug in x equals 1 into the infinite polynomial. Plug in x equals 2 into the infinite polynomial. X equals 7 million into this infinite polynomial, and this will converge. Factorial is way bigger than an exponent. Cool. All right, that is my interval of convergence. Now the radius of convergence is simply half the distance, just like what you imagine the radius to be. Half of infinite is infinite, so not particularly exciting in this case, but true nonetheless. Let's do another. All right, I'm going to give you guys another hint. When in doubt, just do the ratio test. It tends to work a lot for power series. There'll be a couple of times where it doesn't, and I'll show you then, but most of the time the ratio test is going to work nice. So in this example, I'm going to do the ratio test again, which is the limit as n goes to infinity, and I'm going to do the absolute value of a sub n plus 1 over a sub n, which becomes the limit as n approaches infinity of first plug in n plus 1, not for x, but for k, for your counter, and then divide by plugging in n, which is the same thing as multiplying by the reciprocal. And then do some algebra to simplify. This will become the limit as n goes to infinity. I'm going to highlight what cancels. One of the x minus 4 to the n's cancel. And I have an n plus 1 and an x minus 4, and also one of the 2 to the n's cancel. And so I have a 2 on bottom. And then I'm going to take that limit. So this is going to become the limit as n goes to infinity of n plus 1 over 2 times x minus 4. Now I write it that way on purpose because I'm taking the limit as n goes to infinity. So x I don't care about. So I'm going to try to ignore it. And I'm only looking at the limit as n goes to infinity. So as n goes to infinity, what did this become? We missed something. You're right. Oh, I did. Thank you. Thank you. Thank you. Yes, I'm so sorry. There was an extra n on the bottom. I'm so sorry. I'm not going to edit that out. I really am just going to fix that really quick. There's my n over 2n. I'm so sorry. I forgot that n. Okay. I'm taking the limit now as n goes to infinity. And this circled piece right here, if I'm looking just at n, I can do L'Hopital's rule really quick in my head. 1 over 2. So this becomes 1 over 2. Don't forget the absolute value because I don't know what x is. So it's 1/2 times the absolute value of whatever x minus 4 is. And what do I want? Remember, your goal is for the ratio test, I'm trying to figure out where it converges. So I want it to converge. I'm going to force that to be less than 1. And then I'm going to do some more algebra. This is going to take up some space. This one's going to take up some space. Get rid of the 2. Now you have your center and your radius of convergence. This is your center. It was always the center, even from the beginning for that power series. And then this is your radius of convergence. But now I got to figure out the interval. So how do you deal with absolute value inequalities? You go turn it into a compound inequality, add 4 to all sides, and I got x's somewhere between 2 and 6. So my interval is between 2 and 6. Great, fantastic, we're not done. because this is making my ratio test less than 1. That converges fantastic. Remember when the ratio test was inconclusive? If the answer to your limit is equal to 1, you have to find a different test. So we have to find a different test for both endpoints. We have to find a different test for both endpoints. This one's going to be a little bit tricky, and we can do it. I'm going to see how much space I can give myself. I have to look at the x equals 2 and the x equals 6, and each one will have to be its own test. So I'm going to, you might want to just watch for a second, take that x equals 2 and literally plug it in for my x. And then I'm going to have to do a different test, not the ratio test, maybe a p-series, maybe divergence, maybe integral, some other test that's not the ratio test. I have to test my endpoints. So plug in x equals 2, and this is going to become the sum from k equals 0 to infinity of k times negative 2 to the k over 2 to the k, which simplifies, I know we've got a lot on the screen here, the sum from k equals 0 to infinity of k times negative 1 to the k. The 2 to the k is canceled, but the negative did not. And then this is an alternating series. You can test using the alternating series test. This is not, the limit does not go to 0, so it fails the alternating series test. So this, in fact, diverges, and I'm going to say by the alternating series test, it's possible you used a different test and it would also diverge, also fine. Again, test x equals 6. I take that x equals 6 and I plug it into the original. I plug it into here. 6 minus 4 is 2. And so I got k times 2 to the k over 2 to the k. Now the 2 to the k's canceled and there is no negative. Sometimes that happens. This one also diverges by the divergence test, because if you were to take the limit as k goes to infinity of this guy, I got infinity, which is not 0. So that diverges by the divergence test, which means going back to my interval, I already had a radius of convergence. Now I need my interval of convergence. 2 to 6 with parentheses. If one of those converge, you would get a bracket. Ta-da! I have my interval of convergence. Let's do that again, because that definitely is going to require some practice. So I am going to do that again. I'm going to give myself some space for the next one. I realize I didn't give myself enough space. So I'm just going to open up a new page. Same question. I'm going to find the radius and interval of convergence. This was just a small typo. That should be a k right there. I'll fix the colors. There we go. So I have the sum from k equals 1 to infinity of x minus 2 to the k over the square root of k. Let's do the ratio test. When in doubt, let's do the ratio test. It's always going to help you. So my r is going to be the limit as n goes to infinity of the absolute value of, first replace all of those k's with n plus 1, then divided by, replace all of those k's with n, and you know dividing by a fraction is the same thing as multiplying by the reciprocal. Some things are going to simplify, and I have the limit as n goes to infinity. One of those x minus 2 to the n's cancel, and I have x minus 2 to the 1, and I have a square root of n over the square root of n plus 1. When they're both under the square root, I just put one big square root. And then I take the limit as n goes to infinity, and you can do L'Hopital's rule, 1 over 1 is 1, and the square root of 1 is 1. So I ended up with the absolute value of x minus 2. This was the ratio test, so I want this to be less than 1. So now I have that x minus 2 is less than 1 and bigger than negative 1. So x is in between 3 and 1. Now I need to test my endpoints. And I'm going to write that over here to the side. I'm going over here. Now I'm going to test my endpoints. So you're going to test the x equals 1. And you're going to test the x equals 3 with a test that's not the ratio test. I start with the ratio test, then you do something different. So for the endpoints, I'm going to take that x equals 1 and plug it into that x value in the series, and I got the sum from k equals 1 to infinity of 1 minus 2 to the k over the square root of k. And you know that 1 minus 2 is negative 1, so that's negative 1 to the power of k. You can do the alternating series test. Pause the video, find your alternating series test, and do the alternating series test. It passed both of them, it does converge. Okay, if I were to do the test, now I'm going to do the test for x equals 3. So I plug in x equals 3 into the original series, the power series, and I get the sum from k equals 1 to infinity of 3 minus 2 to the k over the square root of k. And you know that 3 minus 2 is 1, and 1 to the power of k is just 1. That's 1 over k to the 1/2. This is a p series where my p is 1/2. It diverges. So that means that my interval of convergence for this series, my interval of convergence was from 1 to 3, where 3 was convergent and 3 was divergent and 1 was convergent. So the bracket includes the converges. Your radius of convergence is half the distance. The distance between 1 and 3 is 2. Half of that distance is, yeah, you got it, 1. Cool. Ta-da. All right. So that's the idea of the radius and interval of convergence. Let's look a little bit more. We already saw that the geometric power series converges for the absolute value of x less than 1. What does that mean? That means that the interval of convergence is from -1 to 1. We don't need to test the endpoints there. Sorry, that's hidden for you guys. Let me try that again. The interval of convergence is from -1 to 1. We don't need to test the endpoints because we already did that when we did geometric. Okay, so let's graph the function and the power series. Let's try to graph the function and the power series and see what happens. And I'm going to try to do that if it lets me. Ooh. Sorry. Oh no. Looks like I've got a fault there. Well, let's open it up though. All right, we got it. So let's graph y equals 1 over 1 minus x. Let's graph y equals 1 over 1 minus x. Okay, so I've graphed it. There's my y equals 1 over 1 minus x. And then I'm going to graph the power series, the geometric power series, which is the sum from n equals 0 to infinity of x to the n. Now, if it were at 25, looks like that's what I got. Let me make that now maybe to n, shall we? Enter. Oh, it doesn't let you do a slider. Oh my goodness. Let's do W. There we go. We'll add a slider. Sorry about that. The website wasn't working. And then I can do more and more and more. Do you see how you add more and they get closer and closer to being the same? Let me show you what I mean by that. This is the graph of y equals 1 over 1 minus x. And then now I have the graph of the geometric and I add more and more terms. It just gets closer and closer to being right on top of each other. But only between 1 and -1. Only between 1 and -1. Outside of that, they're not even close because the power series diverges. Okay, so how can we represent a power series as a function? So 1 on 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. Those two power series are the same, but only for x between -1 and 1. Why would that be helpful? Because then I don't have to add up infinitely many things. I can just plug into a function. Functions are faster than adding up infinitely many things. Or sometimes, not in this case, but sometimes adding up infinitely many things might be faster than finding the function. So it kind of just gives you another way to get the same thing. Okay, so let's do some examples here. Use the geometric power series to find a power series representation for the following functions and identify their interval of convergence. So we are going to take a function and turn it into a power series. And we're going to try to be able to go back and forth. We're always going to want to go back and forth. So does this does this function look kind of like the geometric series? It does. The only difference is this one has an x squared, that one has an x. So that means the only difference is this one has an x squared instead of an x. So that means that turns into the sum from n equals 0 to infinity of x to the 2n. And of course, it only works if the absolute value of x squared is less than 1. Now you can take the square root, though, and of course you get the same interval of convergence. Ta-da. Yeah, cool. So I turned it into an infinite polynomial. You can take a function and turn it into an infinite polynomial. Here's why that might be helpful. An infinite polynomial, this one right here is just 1 plus x squared plus x to the 4th plus x to the 6th and so on. This is only adding and multiplying. I never needed to divide. It's only adding and multiplying. So sometimes we can take a complicated function and make it a little easier, which is kind of cool. Let's do the same thing for part B. Does it look like the geometric series? It does kind of. It's pretty close. It's not identical. My geometric series had a minus. Let's try to find a minus in there. So this will become a 5 times 1 over 1 minus a negative x squared. Now you can see that instead of an x, I have a negative x squared. So that means this turns into 5 times the sum from n equals 0 to infinity of, instead of x to the n, I have a negative x squared to the n, which could turn into the sum from n equals 0 to infinity of 5 times negative 1 to the n times x to the 2n. That is my power series. It happened to have only even powers. It happened to be alternating. And this one only worked for the absolute value of negative x squared less than 1, which if you absolute value of a negative is gone, square root both sides, happens to be the same interval of convergence. Let's do another one. It's not always going to be the same. Let's do another one. So here's my function f of x equals x over 3 minus x squared. Let's turn that into an infinite polynomial, which I really just think is amazing. You can take a division, or in this particular case, a rational function, and turn it into an infinite polynomial, where it's only plus, minus, multiply, like only plus, maybe minus, and powers. It's so much faster. It's super strange that you can do that for all of these rational functions, but here's one we can do it for. So this is going to look like an x squared times the 1 over 3 minus x squared. But if you looked at your geometric series, I needed that to be a 1 minus. So I'm going to factor out the 3 on the bottom. And remember, factoring is a fancy word for divide. So I have x squared over cubed, x squared over 3 times 1 over 1 minus 1/3 x squared, which now that looks like the geometric series, which is the sum from n equals 0 to infinity of, instead of an x to the n, I have a 1/3 x squared, which you could simplify to be the sum from n equals 0 to infinity, and I would watch this if I were you. This becomes x squared times x to the 2n, which is x to the 2n plus 2. And keep watching. This is 3 to the 1 times 3 to the n on bottom, which is 3 to the n plus 1 on bottom. There we go. That is my power series, but this one has some more to it. Remember that your geometric series only worked for the absolute value of x less than 1. But instead of x, I had a 1/3 x squared. Multiply both sides by 3, and my interval of convergence is different. Now I know my interval of convergence is my interval of, convergence is from negative root 3 to positive root 3. the interval of convergence for this power series is different. So this is only going to be a useful power series for x in between the square root of 3 and negative square root of 3. Now you don't need to test the endpoints for geometric series. We already tested the endpoints for geometric series. Let's do another one. Practice makes perfect. This one's hard. This is hard stuff. You want to try to get it to look like a geometric series. That's our goal. We're going to try to get our function to look like a geometric series. So for this one, same kind of thing. I'm going to factor out the x and I'm going to factor out the 2 because we know for geometric series I needed a 1 minus. So when I factored out the 2, I ended up with a 1 minus 1/2 x, which is a geometric series. So I have an x over 2 times the sum from n equals 0 to infinity of x to the n, but instead of x, I have 1/2 x. So let's simplify. You might want to watch. This is an x to the 1 and an x to the n, which is an x to the n plus 1 over a 2 to the 1 and a 2 to the n on bottom, which is a 2 to the n plus 1. Here is my power series representation for that function. But remember, the geometric series only works when the absolute value of x is less than 1. But I don't have x, I have a 1/2 x. I multiply both sides by 2, and now my interval of convergence is from -2 to 2. Ta-da! Okay, so we're just trying to take a function and turn it into an infinite polynomial, and possibly back and forth. Okay, that's really all that we're doing so far. I'm going to leave it at that for 6.1, but I am going to say you're going to use that geometric series a lot. So make sure you're comfortable with that geometric series. Make sure you complete all that homework. Let me know if you've got other questions. This one's going to get a little bit trickier. Geometric series shows up a lot. All right, that's all for 6.1. Thanks.